Hurricanes and tornadoes are two of the most violent types of weather. What are the differences between the two? Storms and violent weather take millions of lives each year. Some of the most destructive storms begin quietly off the coast of Senegal in West Africa. Unremarkable storms warm the ocean and pick up spin from the Earth's rotation. The worst are sent swirling across the Atlantic as hurricanes bent on destruction. At their most powerful, hurricanes spread 1,000 miles across and wheel at 300 kilometers an hour. A storm that size can generate enough power to satisfy the energy needs of the United States for an entire year. Each year, the Caribbean and Florida suffer warnings and near misses. But when hurricanes actually hit, devastation is certain. Richard Herodner courts disaster. He chases storms for a living. Herodner was there when Hurricane Andrew hit Florida in 1992.
The sound was terrific. There were just trees pounding up against the wall. There were cars flipping. There was glass flying all over the rest of the house, shingles being embedded in the walls. It was an hour of just hunker down and hope for it to be over.
Andrew caused $25 billion in damage, and even this paled next to the devastation wrought by Hurricane Mitch's sweep through the Caribbean in 1998.
The biggest danger in a hurricane, and this is where 90% of people are killed, is by the tidal surge. 90% of deaths are caused by drowning in a hurricane.
Tornado Alley in Texas, Oklahoma, and Kansas. These storms twist at 500 kilometers an hour, moving houses and tossing cars in an instant. Here, as many as 1,000 tornadoes a year begin when warm, wet air from the Gulf of Mexico is pushed high into the atmosphere by a cold front moving down from the Rocky Mountains. As the warm air cools, it condenses as a giant thundercloud. The worst thunderstorms produce so much energy, a funnel bursts out of the bottom of the cloud and speeds to the ground. The most violent and destructive touch down as tornadoes. Though most tornadoes exhaust themselves in minutes, they can destroy everything in their path. We've grown much better at predicting violent weather and moving people out of harm's way, but hurricanes and tornadoes still leave destruction in their wake.
Okay guys, so today we are going to talk about weather patterns and severe storms. This is our new unit, and it's kind of interesting because the United States is situated in a place in the world where we actually get to see virtually every type of weather system and weather pattern that anywhere else in the world might see. We have some of the most severe weather of any place. So if you're thinking about, well, I live in Indiana and I know about things like tornadoes and things like that. Well, we also get hurricanes. We get all sorts of weather in America. But yeah, we are definitely in the area of Tornado Alley right here in Columbus, Indiana. So it's kind of important that we know about this stuff, and it's kind of fun to talk about. We're going to focus today on air masses and fronts, which are essentially what brings us most of our weather. Their movement and where they're sitting on the planet kind of determines what temperature it is and how much rain you're going to get, snow, and everything else. This is a photo here from the International Space Station. You can see the station's arm there sticking out with the solar panels on it, and that is a hurricane that is rotating across the surface of the ocean down there. It's spectacular. When you think about how big some of these storms are that are on our planet, it's really astounding. I mean, look at that thing's eye and look at the rotation of it. They can be humongous. Now, we don't deal with too many hurricanes here in Indiana. We do sometimes feel the effects of after they make landfall and the air masses make their way up towards us, we can experience that wet air dumping a bunch of precipitation kind of in the aftermath. So we'll talk about that a little bit next time. But today our focus is on air masses and the general weather that we see here around the United States. So let's start here with air masses. What an air mass is any large body of air that's characterized by the same temperatures and the same moisture content. Okay, so these are big hunks of air that are moving around on our planet across the United States, and they have a similar water content. So there are certain dampness, if you will, and there is a certain temperature. And the interaction of these air masses is what determines whether it's going to be rainy or sunny or what we're going to have. So we're going to talk quite a bit about how they move and what they do on our planet. So the weather in any given area is pretty much determined by the air mass that happens to be sitting over top of it. And you probably have experienced this before when you heard somebody, maybe your parents or somebody, say, hey, there's a cold front coming in, and it's going to get really cold here in a couple of days, and it might be cold for a long time, right? So you've heard these words before. We're just going to kind of describe them some. Here's a quick photo of some tornado damage. We'll talk about tornadoes a bit later. I think I've got this a little out of order, but tornadoes can chuck some things like right through a telephone pole. They're pretty powerful things. So let's dive into some air masses here. Here is what's occurring here in this picture is a cold, dry air mass that came down from Canada and is moving southward. So you probably have heard about, oh, there's a polar air mass coming down and it's going to get very cold. A lot of our cold weather comes from these cold, dry air masses that move down out of the northern reaches up near Canada. And they can drastically drop temperatures really, really rapidly. So sometimes you have an unseasonably cold little period. Recently, this winter, we had a lot of snow, which was kind of a first for us here in Indiana for a long time. And what happened was one of these cold air masses, as the jet stream destabilized, it dipped down and it just sat here, and it got real cold in Indiana. So this does happen, and it'll happen throughout the year. So let's take a look here at how we classify these air masses. We actually have a whole set of abbreviations for describing these things, but by and large, and the answer on your quiz there, is that we classify air masses by their overall temperature, right, and what they form over. So by that I mean, are they warm or are they cold, and did they form over the ocean or did they form over land? That's how we classify air masses. And we have abbreviations for that. Here are all the main types of air masses. You're going to notice that the cold ones are colored blue, and that the red ones are the hot ones. So let's take the cold ones, for example, here first. You're going to see two up there that say MP, and that stands for Maritime Polar. So obviously, this is not hard to remember. Maritime stands for the ocean, right? They formed over water, and the P stands for polar. So think to yourself right here. If it formed over the pole of the Earth, probably cold, right? So this is really easy to remember. If it formed over the water, over the ocean, maritime, it's going to have a lot of moisture that it picked up from the ocean. Now the C stands for continental. So if it's a CP air mass, it's a continental polar. So it formed over the continent where it's drier, and if it's in the P, it's polar, which means it's colder. So you can really sort out the air masses really quick here. An MP is going to be moister, cold air. A CP is going to be drier, cold air. Now, conversely, the exact reverse of that happens down here with the tropical air masses. So the T stands for tropical, so right away think hot, right? They formed in the tropics. And then we've got the M and the C as well. So maritime tropical is going to be very warm, very moist air. Continental tropical is going to be drier, warmer air. Okay, and that's pretty much the whole extent to it. And we're going to look at how these interact and what kind of weathers they cause here. But I've kind of got all the things I just told you on a couple of other slides. So we'll roll through it here and kind of add a little bit more to it. So most of the weather in North America, especially east of the Rocky Mountains. The Rocky Mountains are out west of us, out near Colorado and all that. So this includes us, is influenced by two main air mass types. Continental polar, which comes down from up in Canada, okay, and maritime tropical, which is coming up from the tropics. The collision of these two air masses pretty much right in the smack dab in the middle of North America, in the middle of the United States, controls most of our weather here where we're at in Indiana. So they form out there kind of near the Rocky Mountains, and then they move across the U.S. west to east, and we get hit by them. We can watch it happening on the Weather Channel. You just track them moving right across. If it's raining, you know, over in a few states to our west, we can expect in the next day or two that it's going to be raining in Indiana. That's kind of how it works, right? So let's dig into some of these air masses a little bit more in depth. The first one is the continental polar air mass. And these things they're uniformly cold and dry in the winter. And in the summertime, they're still cold, but they're just not as cold. Makes sense, right? They're colder than the surrounding air masses as well. And they tend to be dry still, right? So they're dry because they formed over the continent, and they're cold because they come from the poles. Now, the maritime tropical air masses, those are formed in the tropics. So right away, you ought to be thinking these things are loaded with moisture. They're down near the tropics. They're warm, especially if they formed over the oceans. They're just loaded up with moisture. Anytime an air mass is loaded with moisture, that makes it inherently unstable. That means it wants to rain. It wants to drop all that moisture out of itself. So then that makes sense, right? If something is really dry, it's going to be more stable than if it's got a lot of moisture in it. So if these things move up and encounter a cold air mass, we will definitely have some storms. Okay. In fact, I have here that the maritime tropical air is really the source of most of the precipitation, the rain, snow, whatnot, that we get here in the eastern two-thirds of the United States. So all that warm, moist air, that's where our water comes from. That's where our rain comes from. Okay, let's keep moving along here. Maritime polar air masses. So these are ones that form over oceans at the poles. So right away, think they're going to be colder, but they will be moister than their relatives, the ones that formed over the continents. Okay, yet not as moist as one that happened to form near the equator in the tropics. And the reason for that is that the warmer an air mass is, the more moisture it can hold. So even though it's a maritime air mass, it formed over the ocean, it won't be able to hold quite as much moisture as one that's warmer than that formed down near the equator. But they are still, like our characterization of them, like in the quiz there that you're taking, is that since they're maritime, they're damper, and since they're polar, they're colder. Okay, so these things, for instance, begin typically as continental air masses. So they usually form over the continent to start with, like in Siberia, and then as they slide out over the oceans, they turn a little bit more mild, and they pick up that humidity. Now they're very unstable, so as they cross the northern Pacific Ocean, they're carrying more rain with them. Okay, more moisture. Maritime polar air masses also originate up in the North Atlantic off the coast of eastern Canada, and those have more of an effect on us. So here's a quick little slide here to show you what's happening. So we've got this one forming way up north here. It's continental polar. It's dry, it's cold, it's stable. But as it crosses the ocean, it continues to be cold, but now it warms just a little bit, and it starts to pick up moisture and become much more unstable, and we classify it as a maritime polar air mass. So now, as you can see, when that thing hits the coast there, it's going to have a lot of water laden in it. So that's how you get things like the rainforest that we have near Washington and up there on our western coast. That's why those things are rainforests, because that cool air, it's cool, but it's containing a lot of moisture. It hits those mountains and gets thrust up, and it just dumps rain. So that's where that comes from. Now, we also have continental tropical air masses. So these are the ones that form over the continents. They're in the tropics, and so that means that they're going to be a little bit drier, but they're going to be warm. Any warm air mass is going to pick up some moisture, but these things, compared to other, tropical air masses that form over the ocean, are going to be quite a bit drier, right? So these things occasionally will affect weather outside of their source region, but a lot of the time they kind of stay put. When it moves from its source region where it formed in the summertime, since these things are very hot and they don't contain as much moisture, they can cause real drought-like conditions, like out in the Great Plains. So if that happens in the fall, it might give us some really mild weather, like in our region, the Great Lakes region. We sometimes refer to as Indian summer. So sometimes you get that weird, oh, it's like summer again here for a little bit. What's happened usually is a continental tropical air mass has moved its way up and sat on our region for a little bit. Let's talk now about fronts. So what a front is, it is the boundary between any of these two air masses. It doesn't matter what kind, it's just that there's always a region between where two air masses meet, and that's where the action is. Pretty much almost any front is going to produce some sort of precipitation. Okay, after the precipitation passes by and the main part of the air mass is sitting on you, then the weather clears up. Okay, if it's a cold front, the cold air is behind it. If it's a warm front, the warm air is behind it. So they're classified by which air is moving in. Okay, so I've got a slide here. Like I just said, a warm front is the front of a mass of warm air that's pushing into some colder air. Okay, a cold front is the front of a mass of cold air that's pushing into some warmer air. So the front is really just a boundary between cold and warm air, but we classify it by which one is moving in. So if it's the warm air moving in, it's the front of warm air. If it's the cold air moving in, it's front of cold air. Pretty easy stuff. Let's look at what they do when they hit us. So here is a warm front. Look on the left there. There's warm air moving in, and there's our symbol for a warm front. You've seen that on a weather map before, I bet. It's a red line there with some little red bumps. That shows you that there's a warm front there. Now, if there's cold air sitting in an area and warm air moves in, what happens is cold air is denser, and so it doesn't want to go up. It sits low. The warm air rams into that cold air and pushes up on top of it. And as the warm air gets lifted, it cools, of course, and cooling warm air essentially squeezes the water out of it, and all that water starts to fall. So warm fronts moving into an area usually give us kind of a light to moderate precipitation, and we can actually see the clouds there. You'll see cirrus to cirrostratus to altostratus to nimbostratus. Those are the types of clouds you see forming as a warm front passes by you. Now, once it's passed by you, you're going to be in a warm mass of air, and the air's, the weather's going to warm up. It's going to clear up. Okay? So, but that's it as it passes over you. Now, let's look at the other side of this. What if a cold air mass is moving in to what was previously warm air? Ooh, now things get exciting. So remember what I said about cold air being denser and heavier than the warm air. When cold air moves in, it makes more of a wedge shape. Okay, it makes this really steep ramp, and the warm air gets pushed up again on top of it. So notice a similarity there. Doesn't matter which air is moving in, the warm air always gets pushed up. That's how it works, because warm air is not as dense as colder air. So the warmer air gets thrust up against this wedge, and it rises rapidly. All that moisture drops out of that warm air, and we get these huge thunderstorms, heavy precipitation, this is the actual thunderhead that you may see, like when you've got a really big thunder and lightning storm. You can see that big cumulonimbus cloud there in the picture. So heavy precipitation, thunder and lightning, that's the entrance of a cold front. And after the cold front passes, you're sitting in a mass of cold air, it's going to be colder out. Okay. Now, there's a couple of other types of fronts. I'm just going to mention them here. They are common, so let's kind of go over them here. The first is a stationary front. So this is what happens when the flow on either side of a front, you've got cold air and warm air, okay, is almost parallel to the line of the front. So it's kind of like the front itself isn't moving, so you can't classify it as a warm or a cold front, okay? And that's why we call it a stationary front. So it's just sort of sitting still. Sometimes stationary fronts can give you long periods of kind of light rain. Another type of front that can also give us some pretty decent rain is known as an occluded front. Okay, this is when you've got these things are rotating. I'll show you a picture here in a second. But what often happens, it's really, really common, is that a cold front will overtake a warm front. So picture in your head, if you will, you've got this warm mass of air moving across the United States, and a cold front catches up to it and overruns it. So like all of the warm air is going to get pushed up into the air. And these are known as occluded fronts when they meet. Let's take a look at what is happening there. So you've got the cold air there on the left in the top picture. You've got cold air on the right, far away from it. So in the middle of all that is this mass of warm air. So to the right part of the warm air, that right there is the warm front. Okay? So the cold front is to the left in front of the cold air, and it's catching up to that warm front, and it's going to meet it. Okay? There's rain at both of those fronts, so when you collide that together, you just produce even more rain, like heavy duty rains for long periods of time, because all of that warm air has been pushed up and it is just coming down and letting loose. So these things can oftentimes move very slowly. They kind of get stuck and stall out, and you get light to like heavy precipitation for like days sometimes when these guys hang out. That's an occluded front. Okay, let's talk about the way these things rotate, because they don't just move west to east across the United States, they also rotate due to the Coriolis effect, because the Earth is rotating on its axis. So here in North America, up here in the United States, we have what are called mid-latitude cyclones. Okay, these are large centers of low pressure that travel from west to east and give us our stormy weather. Here's a picture of one right here. And you can even see its rotation there, moving across the United States. They rotate in a counterclockwise fashion as they go across the United States. And that has to do with the rotation of the Earth, right? Because that's what causes the deflection of the wind in the rotation. Let's look at how our mid-latitude cyclones actually form. Now, in the United States, most of our weather, most of our rain and such, comes from the meeting of a warm front that's coming up from the south that rams into a cold front that's coming down from the north, right? We talked about the cold air coming down from the north and the warm air coming up from the equator. Well, they meet right there smack dab in the middle of our country. So we can actually watch kind of how the fronts are forming there. And you can see what tends to happen is the front kind of takes on this wave-like shape from left to right in the picture as it's being pushed across the United States. Okay? And you can see there what's happened is you've got a warm front and a cold front. And the warm front, or the cold front, is sort of chasing the warm front as it's going. And because the Earth rotates, this thing is going to start to rotate. And the warm air is going around there, and the cold air is going around in a counterclockwise fashion. Okay, and you can see in the picture down there at the bottom, as the cold front lifts, an occluded front starts to form. So we start forming an occluded front as that cold air is catching up to that warm air. Okay, and eventually that thing weakens and pushes off into the ocean. So that's usually how we see weather across the United States. Now, just a couple last little things here. So the airflow that's going on, um, way up high with the jet stream, has a lot to do with how these mid-latitude cyclones get their energy and keep moving. In this next picture you're going to see here, as the jet stream's moving across, you get these situations where you've got high pressure areas and low pressure areas, and the air is rotating. Okay, where the warm air, the low warm pressure air is rising, and the the uh, the colder high pressure air is sinking, and the jet stream sort of fuels that. So when we talk about weird events, like the snow we just experienced over the winter, where we got way more than we're used to, and it got cold for like a protracted period of time, um, a lot of this is caused by the destabilization of the jet stream, and it's a pretty complex process. And you oftentimes hear people say, "Well, how can things like climate change be actually happening when it was cold this winter? Like it got cold, and wouldn't it be getting warm all the time if climate change was occurring and the Earth was warming?" Well, it turns out that one of the effects of a warming planet is the destabilization of that jet stream. And sometimes when it lets loose, it can dip down, and really cold air can plunge across the United States for a long time. And it's a natural process, but usually it kind of rebounds right back. And what climate change has been causing, from what we understand, is those dips in the jet stream have been sitting for longer and longer periods, making certain areas of the globe cold, unseasonably cold for long periods. So don't think that climate change just means that every place on Earth locally is getting hot. Um, you get some very weird weather patterns because of it. So anyway, that's our talk on air movements and fronts. So that's it for today.